Good morning, everyone. I am Sherry Ann Zacharias, Assistant Professor in the Department of Electronics and Communication at Rajagiri School of Engineering and Technology. Today, I'll be discussing on magnetron, which is a kind of microwave crossed field tube, and this is a topic that comes under the Module 2 of the course EC403 Microwave and Radar Engineering. The contents of this presentation are as follows. We will start with an introduction to what are microwave crossfield tubes. Then we will look at the magnetron oscillator, the basic classification. We will then move on to discuss in detail the principle of operation of a cylindrical magnetron and how to derive expressions for the Hull cutoff magnetic equation. And finally, we will conclude by looking at the performance characteristics and applications of magnetron. The reference textbooks are Microwave Devices and Circuits by Samuel Liao and Microwave and Radar Engineering by Kulkarni. So in the last session, we discussed about the two-cavity klystron and the reflex klystron, which are examples of linear beam tubes. So in a linear beam tube, the DC magnetic field is parallel to that of the DC electric field, and that is mainly used to focus the electron beam. In the case of a crossed field device, which is also known as an M-type tube, the DC magnetic and electric fields are perpendicular to each other. So in a crossed field tube, what happens is that your electrons, which are initially emitted by the cathode, they will be accelerated by the electric field between the cathode and the anode, and they will gain velocity. These electrons, due to the presence of the crossed field, will have a tendency to move in a curved path. So only those electrons which have sufficient energy to the RF field can travel all the way to the anode. So this makes M-type devices more efficient in nature. Now we will look at the magnetron oscillator. So magnetrons, basically it consists of some form of anode and cathode that is operated in such a way that the DC magnetic field is normal to the DC electric field that exists between the cathode and the anode. So the basic principle of operation is that it deals with interaction of the electromagnetic waves with electrons which are moving in the presence of this crossed electric and magnetic fields. So the electrons which are initially emitted by the cathode, they are going to get accelerated by the electric field and they will gain velocity. So the greater the velocity of the electrons, the more their path is going to get bent by the magnetic field. So if the DC magnetic field is strong enough, the electrons will not arrive at the anode but return to the cathode, and that causes a backheating effect. Now we will look at the classification of magnetron. Magnetrons can be classified mainly into three types. The first one is a split anode magnetron. So it uses the principle of static negative resistance between two anode segments. So the drawback of the split anode magnetron is that it operates at frequencies much below the microwave range. The second type of magnetron is the cyclotron frequency magnetron. So it operates under the influence of a synchronization between the alternating component of the electric field and a periodic oscillation of electrons in a direction parallel to the field. The drawback is that its output power and efficiency is very low. So in this session, we will be discussing on a specific example of a traveling wave magnetron. So an example of a traveling wave magnetron is the cylindrical magnetron. So here it is based on the interaction of the electrons with a traveling electromagnetic field of constant angular velocity. So the advantage is that it provides oscillations of high peak power compared to the other two types, and it is useful in applications such as radar. Now we will look at the structure of the cylindrical magnetron, which is an example of the traveling wave magnetron. It is also known as a cavity magnetron. So the cylindrical magnetron, it consists of a thick cylindrical cathode at the center and a coaxial cylindrical block of copper, which is known as the anode. So in the anode block, a number of holes and slots are cut, which form the resonant anode cavities. The space between the cathode and the anode is known as the interaction space. So from one of the anode cavities, a coaxial line or waveguide is connected for extracting the output. So the cylindrical magnetron, as I told, it is an example of a crossed field device in which the electric field would be perpendicular to the magnetic field. So here in this case, your electric field between the anode and the cathode is radial, whereas the magnetic field that is produced by a permanent magnet is in the axial direction. So the magnet is placed in such a way that the magnetic lines are parallel to the vertical cathode and perpendicular to the electric field which exists between the cathode and the anode. So this is the structure of the cavity magnetron. So you can see that in the center there is a cylindrical block which is the cathode. Surrounding that you have a coaxial cylindrical block which is the anode, in which you have a number of holes and slots cut. So these form the resonant cavities. A potential is being applied across the cathode and the anode. So there is an electric field that exists between the cathode and the anode, and perpendicular to this structure you have a permanent magnet placed so that the magnetic lines are parallel to this vertical cathode, and from one of the cavities a coaxial line or waveguide is connected in order to extract the output. So this is the top view of the structure, and here A represents the radius to the edge of the cathode and B represents the radius to the edge of the anode. So here you can see this region between the cathode and the anode block. This is known as the interaction space. So these are the anode cavities, and from one of the anode cavities you take out the RF output, and here the magnetic field is in a direction perpendicular to this. Now we will look at the principle of operation of the cylindrical magnetron. So we will first analyze how the electrons behave in the absence of an RF field in the cavity of the magnetron. So depending upon the relative strength of the electric and magnetic fields, the electrons which are emitted from the cathode will move towards the anode through the interaction space following different paths. So here you can see in this figure there are mainly four trajectories shown for the electron. So in the absence of a magnetic field, that is when B is equal to 0, the electron will travel straight from the cathode to the anode due to the radial electric field force which is acting on it. Now suppose if the magnetic field is slightly increased, it is going to exert a lateral force bending the path of the electron as shown in this path B. So the radius of this path is given by R is equal to mv by EB, where V represents the velocity of the electron and B represents the magnetic field strength. So you can see that the radius is directly proportional to the velocity of the electron and inversely proportional to the magnetic field strength. Now, once you increase the magnetic field, at a certain point you will find that the electron will be bent in such a way that it will just graze the surface of the anode and then it will return back to the cathode. So the magnetic field that is required to return the electron back to the cathode after touching the surface of the anode, that is known as the critical magnetic field or the cutoff magnetic field. So if the magnetic field is greater than this critical magnetic field, then the electron will experience a greater rotational force and will return to the cathode faster. So this causes the back heating of the cathode. So these electrons will not reach the anode, but rather it will come back to the cathode. They will spend very little time in the interaction space and then it will come back to the cathode. Now we will look at how the electrons behave in the presence of an RF field. So assuming that the RF oscillations are initiated by some kind of noise transient, the oscillation will be sustained only by the operation of the device. So in order to get sustained oscillation, the total phase shift around the ring of cavity resonators must be an integer multiple of 2 pi, that is n times 2 pi, where n represents an integer. So if 5V represents the relative phase change of the electric field across the adjacent cavities, then 5V is equal to 2n pi divided by capital N, where capital N represents the total number of cavities. So here small n is an integer, so it can take values 0, plus or minus 1, plus or minus 2, etc. plus or minus capital N by 2. So now if the integer n takes a value capital N by 2, then the phase change between the adjacent cavities will be 5V will be equal to pi. So this means that the anode poles are pi radians apart in phase. So in the pi mode of operation, the phase shift between the fields of the adjacent cavity is pi radian. So in this figure, the dotted lines show the electron path in the case of static fields with no RF field, whereas the solid line shows the path of the electron in the presence of RF oscillations. So you can see that the electron A is slowed down in the presence of oscillations. So what happens is that it transfers energy to the oscillation. So it takes a longer time to travel from the cathode to the anode. So these electrons are called the favored electrons and they are responsible for bunching. The electron B, on the other hand, it gets accelerated by the RF field. So it takes energy from the oscillations. So they will spend very little time in the interaction space and it will come back to the cathode. So these electrons are called the unfavored electrons as they do not participate in bunching. So now the condition for maximum transfer of energy from the electrons to the RF field will take place when the cyclotron frequency of the electron is equal to the angular velocity of the RF wave. So the mechanism which leads to the formation of electron bunches and by which your electrons are kept in synchronization with the RF field, this is known as the phase focusing effect. So the number of bunches will in turn depend on the number of cavities in the magnetron and the mode of oscillation. Now two identical resonant cavities can resonate at two frequencies when they are coupled together. This is due to the effect of mutual coupling. So in order to separate the pi mode from the adjacent modes, a method called strapping is used. So in strapping, what happens is that you place small pieces of circular or rectangular cross section which are used to connect the alternate segments of the anode block. So since the resonant modes of magnetron are very close to each other, there is a possibility of mode jumping. So in order to avoid mode jumping, we use the method of strapping. So here in what happens is that alternate anode plates are connected with the help of conducting rings. Okay, this is done in order to separate the dominant mode here, which is the pi mode, from the adjacent modes. But however, a drawback is that strapping may cause power loss in the conducting rings. Now we will look at the equations of electron motion, from which you can derive an expression for the Hull cutoff magnetic equation and the Hull cutoff voltage equation. So in order to describe the motion of an electron in the magnetic field, we know that a charged particle in motion in a magnetic field having a flux density B is going to experience a force which is proportional to the charge Q, the velocity V, the flux density B, and the sine of the angle between the vectors V and B. So that can be mathematically represented as F is equal to QV cross B, that is equal to QVB sine theta. Or F is equal to, you know that the charge of the electron is minus E, so you can write F is nothing but minus E V cross B. So the equations of motion for electrons in a cylindrical magnetron is shown in here as equations 1 and 2. Dou square R by dou T square minus R dou phi by dou T the whole square is equal to E by M ER minus E by M R B Z d phi by dt. Similarly, the second equation is 1 by R dou by dou T R square d phi by dt is equal to E by M bz into dr by dt, where here E by M represents the charge to mass ratio of an electron, which is equal to 1.759 into 10 raised to 11 coulomb per kg, and the magnetic flux density B naught is equal to Bz, and you're assuming that it is in the positive Z direction. So by rearranging the terms of equation 2, we will get dou by dou T R square of d phi by dt is equal to E by M bzr dr by dt is equal to 1 by 2 omega c into d by dt of R square. So here we are using the fact that the cyclotron angular frequency is defined as E by M into Bz. Okay, so the cyclotron angular frequency is the frequency associated with the circular motion of the electron. So by integrating this equation, we will get R square d phi by dt is equal to 1 by 2 omega c R square plus an integration constant. Now, in order to find this integration constant at R is equal to A, where A represents the radius to the edge of the cathode, d phi by dt is equal to 0 because your electrons are emitted from the cathode surface. So by using this condition, when you substitute R is equal to A, this term d phi by dt becomes equal to 0. So you can solve for the integration constant. So you will get the integration constant is equal to minus 1 by 2 omega c into A square. So by substituting the value of the integration constant, we get R square d phi by dt is equal to 1 by 2 omega c R square minus 1 by 2 omega c A square. So from here we can get an expression for the angular velocity d phi by dt. After simplification, we get 1 by 2 omega c into 1 minus A square by R square. Now, since the magnetic field is not doing any work on the electrons, the kinetic energy of the electron, we can write it equal to half mv square is equal to E into V. So that represents the work done to carry an electron in the presence of a potential capital V. Okay, so here the electron velocity, which is this term over here, v square, we know that the electron velocity has two components, the r component and the phi component, because of the fact that your electron is moving in a curved path. Okay, so here from this equation 6 you can write v square is equal to 2 ev by m. Okay, and we know that it has an r component and phi component. So the r component of velocity you can also write it as dr by dt, and the phi component of velocity you can write it as r into d phi by dt. Okay, so now we are going to look at the condition when r is equal to b. So that is, b over here represents the radius to the edge of the anode. So at the edge of the anode, V will be equal to V naught, where V naught over here represents the potential which is applied to the cathode and the anode, and dr by dt would be equal to 0 because of the fact that your electron is just touching the surface of the anode. So by using this condition over here, you can rewrite the equations 5 and 7. Okay, so the equation 5, what you can do is just substitute r is equal to b, and in the equation 7 this dr by dt term becomes equal to 0. Okay, so by rewriting equations 5 and 7, we get d phi by dt is equal to 1 by 2 omega c into 1 minus a square by b square, and b square into d phi by dt the whole square is equal to 2e by m into v0. Now when I substitute equation 8 in equation 9, so you substitute for this term d phi by dt, you will get b square into 1 by 2 omega c into 1 minus a square by b square the whole square is equal to 2e by m into v naught. So by just rearranging the terms, you get an expression for the cyclotron angular frequency omega c, where omega c is given by square root of 2e v naught by m into 2 divided by b into 1 minus a square by b square. Now we know that your cyclotron angular frequency is related to the magnetic field as omega c is equal to E by m into B naught c, where B naught c represents the value of magnetic field for a given V naught for which the electron will not reach the anode. Okay, so by substituting this omega c is equal to E by m B naught c, you can get an expression for B naught c, which is nothing but the Hull cutoff magnetic equation, which is represented as B naught c is equal to 8 times V naught m by E the whole raised to 1 by 2 divided by B into 1 minus a square by b square. So this equation is also known as the Hull cutoff magnetic equation. So it gives you the value of magnetic field for a given V naught for which your electron is not going to reach the anode, okay, but it's going to come back to the cathode. So once you find the critical magnetic field, if the magnetic field B naught is greater than B naught C for a given V naught, we know that the electrons will not reach the anode. So now the Hull cutoff voltage is defined as the voltage that must be provided between the anode and the cathode so that the electrons will just graze the surface of the anode and return towards the cathode. Okay, so conversely, you can write the expression for the cutoff voltage in terms of the magnetic field as V naught C is equal to E by 8m B naught square B square into 1 minus a square by b square the whole square. This equation is also known as the Hull cutoff voltage equation. So if V naught is less than this cutoff voltage V naught C for a given value of magnetic field B naught, it means that the electrons will not reach the anode but it will return to the cathode. Now to conclude, we will look at the performance characteristics of the magnetron. So it is capable of generating a power output of 250 kilowatts in the case of pulsed mode operation, and In the UHF band, it is capable of generating power up to 10 milliwatt and 2 milliwatt for the X band. For in terms of frequency, it is 500 megahertz to 12 gigahertz, duty cycle of 0.1%, and the efficiency that can be achieved is approximately 40 to 70%. Now, the applications where magnetrons can be used, the most popular application is the pulsed radar, which is the single most important application with a large pulse power. It is also used in sweep oscillators, in telemetry and missile operations, and fixed frequency or continuous wave magnetrons can also be used for industrial heating and microwave ovens. Thank you.